You know when you finally find that one perfect tool? Like the one that just effortlessly solves a massive, frustrating problem you've been banging your head against for
Oh,
weeks.
yeah, absolutely. It's the best feeling in the world.
Right. And the immediate, overwhelming human instinct is to just start using that tool for, well, absolutely everything.
Yeah, suddenly every problem looks like a nail because you just bought the world's most impressive hammer.
Exactly.
You see this constantly in software architecture,
Mm.
you know? A developer discovers a paradigm that elegantly handles a heavy workload, and the temptation to unify the entire code base under that one paradigm becomes irresistible.
Because it feels cleaner, right?
Yeah, it feels cleaner. It feels like you've cracked the code.
And that exact instinct is what almost derailed a developer named Aang. So, welcome to today's deep dive. Our mission today is to explore Aang's coding diary from June 11, 2026.
Right, the Access 2 book refactoring notes.
Yeah, specifically this massive refactoring project. The core of this whole thing is a swap in data types. Aang was going through the code base and changing strip text over to lazy text.
Swapping out the standard text imports for lazy ones.
Right, swapping out standard data text imports for data.text.lazy.
Okay, let's unpack this, because what seems like a tiny, extremely in-the-weeds code tweak actually opens up a massive universal question.
It really does.
It brings up this huge question about optimization, resource management, and just how we handle workloads in general.
Yeah, because the stakes are way higher than they look on the surface. Finding a tool that handles the heavy lifting efficiently often tricks us into believing it's universally superior for everything.
A one-size-fits-all solution.
Exactly. But, as Aang's notes reveal, treating optimization as a one-size-fits-all solution is a dangerous architectural trap.
And it's a trap Aang actively had to navigate. So looking at the source, it provides the actual code diff from the refactoring process, the before and after.
We see Aang removing the standard strict text imports and replacing them wholesale with the lazy versions. They're also updating the byte string imports, bringing in modules like data.text.lazy.encoding.
Right, so they are fully standardizing their text usage across this entire XSD ebook program.
Yeah, exactly, which we should probably explain what that program is.
Yeah, the context of what that program actually does is crucial here. So an XS2 ebook converter is essentially a document generation engine.
Right.
It's likely parsing massive amounts of structured data, maybe XML or large style sheets, and rendering out complete, heavily formatted electronic books.
So we are talking about gigabytes of text data flowing through this application.
Gigabytes.
Yeah.
And that is the exact scenario where strict text becomes a total liability.
Really? Why is that?
Well, if you use strict text to process a 50-megabyte book, you're asking the operating system to allocate 50 megabytes of contiguous memory.
Contiguous, like all at once.
Yeah, it has to find a single unbroken block of RAM to hold that entire string at the exact same time.
Oh, wow.
And if you're processing multiple books simultaneously, you will very quickly exhaust the system's memory and trigger an out-of-memory crash. The whole thing just falls over.
Okay. Which is exactly why Aang shifted to lazy text in the first place.
Precisely.
Because lazy text excels at handling large amounts of text efficiently, since it doesn't load the whole file, right? It evaluates the data piece by piece.
Yeah, under the hood, lazy text in Haskell is actually implemented as a linked list of strict text chunks.
Okay.
So instead of one massive block, the program processes a manageable chunk, say 32 kilobytes, writes it to the output stream, and then lets the system reclaim that memory before loading the next 32 kilobytes.
So you're streaming the data rather than swallowing it whole.
Exactly. Streaming is the perfect word for it.
And that streaming capability leads Aang to pose a highly logical question in the diary. They ask, if lazy text can handle large amounts of text efficiently, why not make this the default choice, or even keep it as the only text type?
It's a fair question.
It is. Reading that, the logic feels incredibly sound. I mean, if you own a massive 18-wheeler truck that can haul an entire prefabricated house across the country effortlessly, why wouldn't you just drive it everywhere?
Right.
If you have that kind of hauling power at your disposal, owning a compact car seems redundant. Just take the 18-wheeler.
See, but your analogy highlights the exact flaw in that unified tool logic.
How so?
Taking an 18-wheeler across the country to haul a house is the peak of mechanical efficiency.
Yeah.
But taking that same massive truck down a narrow, winding neighborhood street just to pick up a single carton of milk at the corner store,
Ooh, right?
it's disastrous. You are burning gallons of diesel just to get out of the driveway, destroying the neighborhood's asphalt with your weight,
Yeah.
and you likely can't even navigate the turning radius of a small intersection.
Yeah, the overhead of operating the vehicle completely eclipses the value of the payload. The milk isn't worth it.
Exactly. And Ang's source text explicitly warns against this. The diary notes state clearly that unless you are handling large text for processing, using lazy text for fixed and small-sized text will incur a severe penalty.
Because you're utilizing a massive piece of machinery for a microscopic task.
You are. It's just inherently wasteful.
So, to understand why that massive truck is so detrimental for those small neighborhood trips, we need to look under the hood.
Yeah, let's get into it.
We have to move from the philosophical concept of laziness into the mechanical reality of how lazy evaluation actually operates in a computer's memory. And Eng's diary introduces a fabulous technical term for this mechanism.
The thunk.
The thunk. It sounds like a heavy weight dropping on the floor, which honestly feels appropriate for what it does to a system.
It really does. The thunk is the foundational building block of lazy evaluation. Ang defines it in the notes as an evaluated later pointer.
An evaluated later pointer. Okay, so a thunk is essentially a computer's version of an IOU.
I like that.
Let's visualize this for you, the listener. If someone owes you $1 million in physical cash, that is going to be incredibly heavy.
Oh, massive. We're talking suitcases full of bills.
Right, suitcases. It's a security risk, it takes up a ton of physical space, and it's difficult to transport. In that scenario, an IOU, a single piece of paper saying I owe you $1 million, is infinitely lighter and easier to carry around than the actual cash.
Which is your lazy text handling a massive document stream.
Exactly.
But what's fascinating here is how that IOU translates mechanically. In a compiled language like Haskell, a thunk isn't just a magical sticky note. It's a closure allocated on the heap.
A closure on the heap. What does that mean in plain English?
So when the program creates a thunk, it allocates memory for a pointer to the actual code that needs to be executed later, plus, and this is the kicker it has, to capture and store the entire environment.
Wait, the entire environment?
Yeah, it bundles up all the variables and context necessary to perform that computation whenever the system finally asks for the result.
So you're packaging up an entire state of the universe just to evaluate a string later.
Exactly. For $1 million or a 50 megabyte text file, packaging up that context is a brilliant trade-off.
Right, because the text file is so huge.
The pointer and the environment take up a fraction of the memory the actual file would consume. But consider the alternative scenario. What if someone owes you a single penny?
A penny? Okay, well, if they just hand you the penny, the transaction is over in a millisecond. The penny is tiny, discrete, and immediate.
But if they insist on using the lazy approach, they don't hand you the penny.
Because they have to use the IOU.
Right. They hire a lawyer to draft a complex, notarized IOU contract. They define the legal parameters of the penny, secure signatures, and file the paperwork in a massive filing cabinet.
That is hilarious. The physical contract is vastly larger and heavier than the penny itself.
The effort to create the promise takes up more space than the actual asset. And Ang states this directly in the notes. The memory head of handling small text is way more than the actual text data itself.
Wow. So you are generating administrative overhead for a payload that could have been resolved instantly.
Yes, the system has to allocate memory for the pointer, store the execution instructions, and maintain the surrounding environment data. You are crippling your system's efficiency with paperwork.
Okay, wait, I have to stop you there.
What's up?
Here's where it gets really interesting, because Ang mentions memory leaking issues as a direct consequence of this, and that feels, I don't know, entirely contradictory to me.
Contradictory how?
Think about the core philosophy of laziness. If a system is quote-unquote lazy, it is fundamentally holding off on work. It's conserving its energy until the absolute last second.
Sure.
How does doing less work actively cause a memory leak?
Yeah, it seems counterintuitive until you look at how memory is actually reclaimed by the computer. A memory leak in a lazy system doesn't happen because the computer's doing too much heavy lifting.
Okay.
It happens because of graph reduction and pointer chasing. We need to look at the garbage collector, the GC.
There's no GC.
The GC's job is to traverse the computer's memory, figure out what data is no longer reachable by the program, and sleep it away to free up RAM.
So it's essentially auditing the system to see what can be thrown out.
Think of the GC as a highly meticulous bookkeeper auditing a massive corporate ledger. When this bookkeeper comes across strict text, their job is incredibly easy.
Because the strict text is just right there.
Exactly. Strict text is literal data sitting directly in memory. The bookkeeper looks at it, checks if the active program is still using that specific string, and if not, they instantly cross it off the ledger. the memory is freed.
They see the penny, nobody needs the penny, they toss the penny.
But when that bookkeeper comes across a thunk, an uncached IOU, the audit just grinds to a halt.
Because it's not the actual data.
Right. The thunk is a pointer. It says the data isn't here, it's over there, and you need to run this equation to figure out what it is. The bookkeeper now has to trace that pointer across the ledger. And what if that thunk references a massive data structure in its captured environment?
Oh, because the thunk needs that context to eventually run, the system isn't allowed to delete the context.
You nailed it. The GC sees that the thunk is still technically alive, which means everything the thunk points to must also be kept alive.
Even if the program doesn't need it anymore.
Even if the main program has logically moved on and will never actually ask for that text to be evaluated. The mere existence of the unevaluated pointer forces the system to hold on to the underlying data.
That is the memory leaking issue, where data held in memory becomes outdated. The system is just holding on to ghosts because the pointer told it to.
Yes. This is notoriously called a space leak in lazy evaluation. And they are incredibly difficult to debug because the stack trace doesn't point to where the memory was allocated, it points to where the thunk was finally evaluated.
So your system's memory slowly fills up with this outdated, tangled web of pointers.
Exactly. The GC is burning massive amounts of CPU cycles, just chasing these pointers around trying to figure out if it's legally allowed to delete anything.
Your system runs out of memory, not from the workload, but because it's drowning in administrative paperwork from a million tiny tasks it promised to do later. That is wild.
It is, whereas strict text forces the issue. It evaluates immediately. It does the computational work up front.
So the bookkeeper knows what to do with it.
Exactly. The GC sees exactly what the data is, knows exactly when it's no longer needed, and cleans it up immediately. The burden of tracing dependencies is vastly reduced.
So what does this all mean for you, the developer? We've explored the theory, we've broken down the architecture of a thunk, and we've seen the catastrophic space leaks. But how does Eng actually operationalize this knowledge?
Well, Eng wraps things up pretty nicely.
Yeah, the source text concludes with a highly practical cheat sheet. It draws a very clear line in the sand regarding scale.
The cheat sheet is a masterclass in contextual engineering. Eng explicitly lists the use cases where strict text is mandatory.
Like what?
Things like short or medium strings, configurations, JSON keys, database records, and identifiers.
Okay, let's take a JSON key as an example. Something like the word username in a web payload. It's what, an 8-character string?
Right. And in a high-throughput environment, an API might be parsing 10,000 of those JSON payloads a second.
Wow, 10,000 a second.
If you use lazy text for that, you are actively instructing your compiler to allocate 10,000 heat closures, capture 10,000 local environments, and generate 10,000 thunks every single second, just to hold the word username.
You are burying the bookkeeper in IOUs for 8 bytes of data. It's absurd. Using a lazy text approach for a tiny JSON key is like, it's like hiring an executive architect to build a 10-piece Lego set.
Yes, the architectural overhead completely dwarfs the construction.
The architect is going to spend 3 weeks drawing up blueprints, securing zoning permits, and conducting a site survey, just so you can snap a red plastic block onto a blue plastic block.
It's madness. And if we connect this to the bigger picture, Eng's diary reveals a profound truth about optimization that extends far beyond Haskell programming.
Oh, definitely.
Efficiency is never about finding one perfect universal tool. The silver bullet is a myth. True performance is derived from recognizing the context of your data.
Which brings us to the second half of Eng's cheat sheet. You use lazy text when handling large files, streaming data, or document generation.
The exact scenario of the XS2 book program.
Right.
When you are streaming gigabytes of data to render an EPUB file, you need the 18-wheeler. You need the ability to hold an IOU for a chapter of text so the operating system doesn't panic, trying to allocate a massive contiguous block of RAM.
So it's about balance.
Completely. Performance isn't strictness, and performance isn't laziness. Performance is the architectural discipline of knowing exactly when to force immediate evaluation and exactly when to defer it.
It's about respecting the scale of the problem in front of you. Man, what an incredible technical journey from a single diary entry.
It really is a lot to pull from one refactor.
It is. We started with a routine refactoring where Eng swapped out strict text for lazy text. That led us to dismantle the silver bullet fallacy, the trap of using your heaviest tool for your lightest problems.
We examine the anatomy of the thunk, realizing that a deferred computation isn't free. It's a heap-allocated closure that demands its own memory.
And we watched the garbage collector struggle to audit a ledger filled with uncached IOUs, resulting in space leaks that slowly strangle a system's memory.
And finally, we arrived at Eng's practical cheat sheet. Strict evaluation for discrete data points like JSON keys, and lazy streaming for massive document generation.
It all comes together so perfectly.
Before we wrap up, I want to leave you, the listener, with a thought that builds on the underlying philosophy of the thunk.
Oh, I like where this is going.
We've spent this entire deep dive analyzing computer architecture and memory allocation, but consider your own human operating system. Think about the mechanics of human procrastination.
Oh, wow, that's an interesting pivot.
How often do you create mental thunks in your own brain for tiny, discrete 5-minute tasks?
Oh, all the time.
Right. You see a quick email you need to reply to, or a bill you need to pay, and instead of just evaluating the task strictly in the moment, you create an evaluated later pointer. You tell yourself, I'll handle that this afternoon.
You generate a cognitive IOU.
Exactly. And you have to maintain the environment for that IOU.
The mental context.
Yes. Do we suffer from our own cognitive space leaks? Because the mental overhead of remembering that you have to do that tiny task later, the stress of holding that outdated pointer in your working memory while you try to focus on other things, might actually be heavier and more exhausting than just strictly doing the task right then and there.
Because your mental garbage collector is burning cycles, tracing tasks you deferred.
Exactly.
Are we using an 18-wheeler to carry a carton of milk in our own daily routines? Man, what a phenomenal question to end on.
It really makes you think about your own processes.
It definitely does. Well, thank you so much for joining us as we explored Eng's notes. I highly encourage you to take a look at your own workflows, both in your code and in your daily life, and ask yourself where you might be generating too many uncached IOUs.
Good luck clearing out those mental thunks.
Until next time, keep exploring, keep questioning, and maybe try being a little more strict with those mental pennies. Take care.